Welcome back. We will continue our discussion on viscous flows, and we have seen in the last lecture that for the Navier-Stokes equation, when we make assumptions of the flow being steady and fully developed, we arrive at an equation where you have a balance between the viscous force and the pressure gradient in the direction of the flow, and then if there was a body force present, it would be balanced by a pressure gradient. So now we will consider different forms of this to actually look at various steady, fully developed flows. And the flows that we have in mind are also unidirectional, which means it's flowing only in one particular direction. So the x momentum, so if I design a flow where the flow is occurring, so I'll look at for the time being flows that are internal flows or flows which are confined by boundaries. You have a direction of motion that is x. So if we write down our governing equation, then our governing equation is 1 by rho dou p dou xi plus mu dou square u dou y square. This is in the x direction. So this is our governing equation that we have. Now if there is no body force in the problem, then you have minus 1 by rho dou p dou y is equal to 0. So in absence of any body force, this is my governing equation. So we'll first work out some classical problems to understand what the velocity profile looks like. You might have already seen this in any introductory course in fluid mechanics, but we will go through this exercise because it will help us get a feel of what is happening when we are looking at this balance, and then when we relax the assumptions that we are making, it will also help us put into context the steady state solutions that we are looking at. So the first problem that we will do is the problem of motion of a boundary. So I need to initiate a motion. So one way to do that would be I move, let's say, the top plate with a given velocity and the bottom plate is held stationary. So the top plate is moving. So u is equal to u bar at the top plate and u is equal to 0 at the bottom plate. And the gap is h. So I will say this is a y coordinate, y equals to 0 and y equals to h. So this is a configuration where I move the top surface with a certain velocity, and then I try to actually understand that what would be the velocity field that is being set up due to the governing force balance that I have. So in the y direction, I have 0, 1 minus rho dou p dou y, which means pressure is purely a function of x. There is no y variation of pressure. So pressure is only a function of x. Now if I arrive at the second equation, then I have the second equation is minus 1 by rho dou p dou x, which is the x momentum equation, mu dou square u dou y square. Now I am not applying any pressure gradient in this problem. So there is no imposed pressure drop in the problem. The problem is driven based on the motion of a boundary. So since I am not applying any additional pressure at the inlet or outlet in order to drive the motion, I will look at a scenario where there is no pressure gradient in the x direction. The flow is purely driven due to the motion of boundary. So in which case it's dou square u dou y square is equal to 0, and u is not varying in the x direction, which means this is just an ordinary derivative. So d square u dy square is equal to 0, and that gives us a velocity field which is a constant plus a linear function. So when you integrate this, you just get this particular solution. Now you have a boundary condition to satisfy. Now what are the boundary conditions? So the bottom plate it's stationary. So at y equals 0, u is equal to 0, which means a plus is equal to 0, and that gives me a is equal to 0. Now at the top plate, the plate is in motion, so u is equal to y equals h equals to 0, and now you have a is obviously 0. So then I have b times h, sorry, this is u bar, the plate is in motion, so that is u bar, which gives me b is equal to u bar by h. So which gives us a velocity profile that is u bar y by h. So if you draw the velocity profile, there is a flow in the x direction that is varying linearly with the vertical coordinate. So there are various names for this problem. This is known as the plane Couette flow, or also simple shear flow. We have seen this problem earlier in other contexts of kinematics, where we tried computing streamlines, vorticity, velocity gradient, etc. So this is the simplest problem that you can think of, where there is a straining motion in the problem, there is a deformation in the problem, because the velocity varies transverse to the direction of motion. So if you were to think of looking at a fluid element here, so if I just consider a fluid element here and mark them as points A and B at time t equals 0, the point A and B at a later time, they are not going to lie along the y axis, they are going to tilt. So they are going to rotate and they are also going to stretch. So this is effectively a signature of a deformation that is going on, as well as the fact that there is vorticity in the problem. So this problem is also has, even though the streamlines are all rectilinear, they are all parallel to the x-axis, you do have vorticity in this problem because neighboring fluid particles are moving with different velocities. So you have a rotational part to this problem. So you have studied this in some detail when we were trying to think of kinematics. But a point which is important to note here, that now that you have started doing viscous flow, what is the significance of this solution if I were to plug this into my inviscid equations? So if you remember, your inviscid equations were rho, dou uy dou t, uj, dou uy dou xj minus dou p dou xi. I am ignoring any body force. Now there is no pressure gradient that is applied in this problem, so I don't have any pressure drop. A constant pressure is basically going to be sufficient. And if I write down the x momentum version of this, that is dou u dou t plus u dou u dou x plus v dou u dou y is equal to 0. Now if you plug the linear version of this, so you take this solution, you take the plane Couette solution and you plug it into this, you will see that this is a solution of the inviscid equation. Right, it trivially satisfies. So Euler's equation, the plane Couette flow, is basically a solution of Euler's equation. Now this is where you need to start thinking a little bit more about viscous effects. So the velocity field that we obtained satisfies Euler's equation. But if you were to think of what would happen if the fluid was inviscid, I start moving my top plate. So think of it as an unsteady problem. We will work this out also as a complete unsteady problem. But before we do a formal calculation of the unsteady problem, think of what is going to happen in the unsteady problem. So in the unsteady problem, you have a top plate which at time t equals 0 starts to move with a certain velocity. Initially both the plates are stationary, and then you turned on the motion of the top plate, it is set into motion and it starts off with some velocity that you have prescribed at time t equals 0. So the fluid initially, which was occupying this gap, was at rest. So the velocity here initially was at rest. Now if you did an inviscid calculation, the top plate moves with a velocity u equals to u bar, bottom plate is stationary. The fluid which is in between will continue to be in a state of rest. Because the only way you can actually set an inviscid fluid into motion is through normal motion of a boundary. A tangential motion of a boundary will not set an inviscid fluid into motion, because an inviscid fluid is allowed to slip. So, if you only introduce tangential motion of boundaries, there is never going to be any motion if you are strictly treating the problem as an inviscid problem. Because the fluid layer which is sitting here, those fluid layers, I am exaggerating this and drawing it as fluid molecules, those fluid layers can slip. They are not obligated to stick to the surface. So, even though you have started moving the plate, the fluid that is confined between the two plates have no reason to move. So, even though the Couette flow solution satisfies Euler's equation, you will not get the Couette flow equation without including viscous effects. So, that is the important part. See, when you saw the solution of the Couette flow equation, the solution of the Couette flow equation came by equating your viscous force to 0. Right? You said that the viscous force is 0, and by equating the viscous force to 0, you obtain a velocity field that has a linear variation. Now, viscous force being basically 0 implies that your shear stress is a constant everywhere in the problem. So, a constant shear stress, so if I write down my component of sigma xy, so sigma xy will be mu dou u dou y plus dou v dou x. This is 0. Dou u dou y is non-zero. So, you get mu u bar by h. So, the shear stress in the entire fluid is a constant, which is why the viscous force is 0. Because the divergence of the shear stress gives you the viscous force per unit volume. So, the shear stress remains constant from the bottom plate to the top plate. So, this aspect that when you are shearing the top surface, the entire fluid is set into motion is only possible because of viscous effect. So, if you do a viscous problem, and again repeating my point that we are going to look into this unsteady problem a little bit later, but you are going to get velocity profiles which will look something like this. That initially the velocity profile will only be the fluid close to the top plate being set into motion, and gradually if you wait long enough, you are going to arrive at the linear profile. So, this is just like a die problem that we keep discussing, that if you imagine releasing a sheet of dye at the top layer. So, initially you take blue dye and you put it on a sheet or on a layer on the top. Now, that dye is going to diffuse. It is going to diffuse and spread into the bulk. And if you wait long enough, it is going to spread entirely. Now, if you say that the concentration of the dye is held fixed at some concentration at the top and it is some other concentration in the bottom, then that dye concentration is going to adopt a linear profile. The same is applicable for temperature. If you have a top plate at a given temperature, bottom plate at some other temperature. So, imagine there is a hot plate and then there is a cooler plate. Now, initially what would happen, that the fluid which is attached to the hot plate will start to warm up. Why is it warming up? That is due to thermal conduction. There is no motion in the problem. So, purely due to thermal conduction, the fluid layer which is close to the hot plate starts to warm up, and gradually the temperature profile in the fluid will be a linear temperature profile, or what we call as a conduction profile, that goes from the hot plate to the cold plate. And this has been enabled by thermal conduction. So, in the same way, the fluid that is occupying the two plate, when you are trying to move the two surfaces differentially, which means that the bottom plate and the top plate are not moving with the same velocity, you are trying to shear the fluid. So, if you think of the fluid as made up of, in an exaggerated sense, as being made up of a bunch of spheres. So, if you do this kind of a cartoon, if you think of the scenario being completely inviscid, I can drag the top plate and all the spheres will stay just the way they are. There is no friction in the problem. So, if there is no friction in the problem, I am doing a tangential motion, it can nicely slide over. There is no reason for the spheres to be set into motion. But if these were rough spheres and the boundary also was rough, there is friction that is there in the problem. The moment I drag this, I am setting into motion the spheres that are closest to the wall. So, they will start to move, and then they will make the next layer of spheres realize that there is some motion that is happening. So, what viscosity is doing here, viscosity is acting as an agent of momentum transport. We always think of friction, or in this case viscosity, as something that damps the motion. I would like to move in a certain way, and what viscosity is doing is it is slowing me down, it is dampening my motion. But when you think in terms of fluid, viscosity plays a very important role in transporting momentum, which if you first think of it, it appears a little counterintuitive. That something that was at rest can only be brought into motion because of viscosity. If there was no viscosity, there would not be any motion in this problem, because I am just doing tangential motion. So, if I am doing sliding motion, there is no way the fluid should be in a state of motion. It is enabled because of viscosity. So, this is a carrier of momentum from regions of higher momentum to regions of lower momentum. And this is why it is very important to think of viscous effects in terms of momentum transport, rather than just thinking of them as I have motion and it is just slowing me down. Which is true, it does slow you down. It will, if you try to have a problem where you drop a ball and you do it in vacuum, you do it in air, you do it in water, you do it in honey, you for the same mass, you are effectively going to obtain different terminal velocities. That is not ambiguous, that is reasonably well accepted. So, it is having a retarding effect or a decelerating effect on the problem, it is slowing you down. But then this part is actually very important, that it is also playing this role, that by the same property of friction, it is playing the role of transporting momentum. When you do a rigid body, when you are trying to slide a rigid object, then the only role that viscosity is playing is slowing the motion down. But when you do a deformable object, by virtue of slowing you down, it is actually setting motion into the system. Otherwise, there would be no motion. So, if you have the same, this Couette problem is very instructive, that if you had a rigid object here and you try to slide the top plate, friction is going to resist that motion. If there is no friction, then the entire block will move with a velocity u, if you push the block. If the block was stationary, then the block would remain stationary if there is no friction. I can have two surfaces attached to a block, move with any velocity I want. If there is no friction, they can slide. It's friction which will basically stop because of friction, there is going to be a certain amount of resistance to this motion. Now, when you say this is not rigid, but this is a deformable medium, you can think of this as slices. You can think of them as slabs of rigid body. A loose way of thinking of the fluid is as if there is a stack of rigid body, each having a friction coupling between themselves. So, when you try to slide the top slab has to adhere to the frictional connection with the top surface, and then it is going to make the next one move, the following one move, and subsequently that is how the transport is happening. So, this idea that thinking beyond the velocity profile, that viscosity is essential for momentum transport. And primarily, this is the only way you can transport momentum in the tangential direction. When you are shearing surfaces, the only way that you can make layers move or set into motion is possible due to viscous effects. So, this is a crucial way for how you should be thinking of the role of viscosity in a fluid. So, we had this particular problem. So, we have a plane Couette flow that we worked. We will take up. Yes.
Typically, I can understand that viscous, if there is inviscid flow, there it will be not same profile like viscous flow. But mathematically, in the velocity profile, there is no viscous term. So,
Correct.
If I just do math, so if I understand by the math, so how can I understand that viscosity has big role to that kind of
In inviscid problem or viscous problem?
viscous problem? I mean, in that inviscid solution, there is no viscous solution. There is no mu, right?
Mu is there. Well, the velocity profile here doesn't have a mu, but shear stress will have a mu there. So, there is a constant shear stress, and constant shear stress basically is coming because you have a linear, or rather constant shear stress basically is connected to a linear velocity profile. So, in this case the velocity profile doesn't have a mu present. That is because you are saying viscous force is 0. So, because viscous force is 0, any any value of viscosity will give you the same velocity profile, but the shear stress corresponding to different fluids will be different, because the shear stress will depend on the value of viscosity. So, that was about motion set through boundary, where we were having the plates move. Now, we will have a motion that is set in by having a pressure drop. So, I will apply a pressure drop. So, you have a higher pressure at the inlet and a lower pressure at the outlet. And if you go back to your earlier description, the equation that we were solving for was mu dou square u dou y square minus 1 by rho dou p dou x and minus 1 by rho dou p dou y is equal to 0. So, now this tells us that p is purely a function of x, it is not a function of y, which is to say that in the equation for, if I write down my x momentum equation, I have mu dou square u dou y square is equal to 1 by rho dou p dou x. Now, pressure is purely a function of x, it is not a function of y. U is only a function of y and not a function of x. That is coming from fully developed assumption that there is no variation of u, or for that matter any velocity component in the x direction. So, this is purely a function of y, this is purely a function of x. Now, that is only possible if they are equal to some constant. Right, the only way you can have a pure function of y and a pure function of x being equal to each other, if those functions take the trivial form of being a constant. So, 1 by rho dou p dou x is a constant, which gives me d square u dy square is equal to one minute, I think I have, yeah. So, I am writing it in terms of u, mu. So, there will not be any 1 by rho, yeah. So, there is no 1 by rho here, because I am using the dynamic viscosity. Yeah. So, I have 1 by mu dp dx, this is a constant. So, now if I integrate, I have a plus by, that is the homogeneous solution, plus 1 by mu dp dx y square by 2. Okay. So if you apply the boundary condition, so we have a problem where at the top plate at y equals 0, no slip boundary condition, no penetration boundary condition. At the top plate y equals to h, it's again the same no slip and no penetration boundary condition. So when I substitute it into this equation, I will have 0 is equal to a plus b times 0 plus 1 by mu dp dx times 0, which gives me a is equal to 0, that is at the bottom plate, and at the top plate I will have 0 is equal to a plus bh 1 by mu dp dx h square by 2. Now a is 0, so this implies b is equal to minus 1 by mu dp dx h by 2. So we substitute and we obtain the relation that minus 1 by mu dp dx y, I'll take the 2 outside, h minus y. So that is your velocity profile when you have a pressure drop at the two ends. So you have a, if now you say that I have a higher pressure here, so P2 or rather P inlet is higher than P outlet, that means my minus dP dx is a positive quantity, because this would be P in minus P out by the length. So this is del P by L, where del P is the inlet pressure minus the outlet pressure. So I can write this as del P by L into 1 by 2 mu y h minus y. So here the flow is in the positive x direction. If you have the pressure on the right hand side being higher, then the flow will be moving towards the left. So this is your plane channel flow. It's again a very classical problem where the velocity profile takes this parabolic form when you have a pressure drop that is given in the problem. Now you can once again revisit this problem and ask what would happen if you were to do this problem as an inviscid problem. So the solution that we have worked out, if you plug this particular solution, so you have said that I have a pressure gradient which is driving the problem. So if I apply a dP dx into my problem and you go back to your equations, so if you apply a dP dx and if you ignore the governing equation, ignore the viscous part of the equation, then if there is a pressure gradient that you are applying, that pressure gradient can only be balanced if you have an advective nonlinearity. You need an advective nonlinearity in order for you to have a solution. So the moment you apply a pressure gradient, you will have u dot del u, require a u dot del u to balance that pressure gradient. So in this particular case, when you are doing the channel flow problem came about by precisely doing a balance between the viscous forces and the pressure gradient. So there is a pressure drop that is applied. So when you are applying a pressure gradient, now what would you expect in a usual setting if you think from the point of view of Bernoulli? What would be your expectation if you go back to your inviscid picture, that if there is a pressure drop across a streamline. So if I draw a streamline, there is a high pressure here, there is a low pressure there. What would be the expectation from inviscid theory? Velocity should increase. So I should get acceleration. So as I was saying, that the term that is there is u dot del u, which is balanced by grad p, right? This is what we write down in terms of Bernoulli. When you take a gradient of that, you can write this as gradient of P by rho plus half U square is equal to U cross omega. And then you say that along a streamline, this particular quantity is constant. So you will have P by rho plus half U square is a constant along a streamline. So in this particular setting, if you had a channel flow and you applied a pressure gradient, which means the inlet pressure was higher than the exit pressure, then the flow has no other option other than accelerating. Now, the reason that you are not getting an accelerating flow is what we are calling as a fully developed flow, that there is no variation of the flow as you move along the direction of the flow. And that is happening because the pressure gradient or the force applied by pressure, that is being exactly compensated or balanced by viscous effects. So in the complete problem, what you have is u dot del u minus grad p mu del square u. This is the full steady state equation. So when you are thinking of a channel flow problem and you say that I have a pressure drop that is applied, the balance between inertial forces and pressure gradient will give you a velocity profile that is going to accelerate. If it is just u dot del u balancing minus grad p. So think of this now as a problem which is evolving in space. We use the word fully developed. So now you relax that fully developed and think of an evolution in space. So when it is an evolution in space, because the channel in a real life problem is finite length, it is never infinite length, which means there is an inlet, there is an outlet. So at the inlet you have a high pressure, there is a lower pressure. So when you apply a higher pressure, the fluid enters the inlet. So the moment it has entered the inlet, immediately at the entry point, it has basically started to experience a balance between your inertial and pressure gradient forces. But then there are these walls, and this is how you have to always think in terms of momentum transport. The walls are immediately going to bring the fluid to a halt for the layer which is attached to the wall. So if you think of splitting the problem into an inner region and an outer region, a region close to the wall and a region away from the wall. There is a core and then there is a wall region. The fluid layers which are close to the wall, they cannot ignore viscosity. They have to immediately accept the fact that there is a certain stickiness of my boundary. So I cannot slide over the boundary. So you have introduced a fluid, you have applied a pressure gradient, the fluid starts to rush in. Now the layers which are sticking to the wall, they have to instantaneously slow down. Whereas the core or the inner region, that is kind of oblivious to viscous effects. It doesn't really care about viscous effects. So it is going to move as if it is governed purely based on inertial effects and pressure gradient. And then gradually the information of the wall is going to percolate. The fact that there is a wall is creating diffusion of momentum. So here there is no momentum source that is there at the wall. The wall is not a momentum source, you are not moving the wall. But what the walls are basically doing is that you cannot arbitrarily take the fluid and make it move with an accelerating nature in the core. The moment you are doing that, it has to spread out that momentum. That is what viscous effects are doing, right? So you have a room and imagine that the room is packed with students. The students in the middle of the room, they start to rush out of the room. So as they start to rush out, they cannot just run out at an arbitrary speed because they have neighbors who have not yet started to move. So you are basically letting students exit a room from the middle. So as they start to run out, their adjacent neighbors will gradually start to move. But eventually the ones who are just sitting at the wall, if you think of this idealized example, they can never leave that classroom. They are kind of stuck because they are exactly at the wall. So gradually what you will happen is, you will observe is that the ones which are at the center, they will get slowed down at the expense of their neighbors, because they cannot move as fast. So finally you will arrive at an equilibrium state where you will stop accelerating and you will get an exact balance between the pressure gradient force and the one that is due to viscous effects. There is no further acceleration. So the acceleration continuously keeps decreasing, keeps decreasing, keeps decreasing, keeps decreasing till you arrive at a fully developed state, which is precisely where there is no further acceleration. Because when I said fully developed means that dou x of the fluid velocity is 0, another way of thinking about that is that when it is fully developed, there is no acceleration of the fluid. U dot del u is 0. So the acceleration continuously keeps decreasing. Eventually, it vanishes off when there is a balance that you have reached, or an equilibrium that you have reached between viscous force and pressure gradient. Because if this was perfectly a Bernoulli problem, governed by inviscid theory, along a streamline, I should have the fluid accelerate. The velocity should be higher at the outlet than it is at the inlet. Right? That is, there is no disagreement on that. Here what we are saying, the velocity on that particular streamline is exactly the same everywhere, which means that there is no acceleration because the viscous forces are exactly in balance with pressure gradient force. So you can always work these algebra out and get the parabolic profile. But what I want you to always think is a little in advance in terms of what is the reason for arriving at this velocity profile and how do you arrive at this velocity profile thinking of an evolution. In the plane Couette problem, you thought of it as an evolution in time. Right? In the linear problem, linear shear problem, you had a top plate moving and you thought of the problem as something that was evolving in time. Right now in the plane channel problem, you are thinking of a spatial evolution. So the two assumptions that we are making, steady and fully developed, we are going to get into detail and work it out when these assumptions are removed and we do a problem that is unsteady and a problem which is also developing. But when we are doing this right now, it's also important to actually take a note of what is it that is going on in terms of force balance. We are not working out exactly the velocity profile where all the three terms are there, but you can start to anticipate that what is actually going on. So instead of thinking of this problem as being driven by a pressure drop, you can also think of this problem as being driven by a flow rate. So how can you do a pressure drop experiment? So you have a pipe and imagine that there is a head of water here. Right? Now, so there is a pressure, hydrostatic pressure head here, and this is where it is exiting. So that naturally gives you a pressure drop. You can play with that water level and you basically can actually maintain a certain del P which is driving the motion. You can also do the problem where you inject the flow at a given flow rate, which means you are pumping liquid into a pipe and you are doing so at a fixed flow rate. So which is to say that you can calculate what is the flow rate. So the flow rate would be 0 to h u, the definition of the flow rate is u dot dA. Now here this is a unidirectional flow, so our life gets easier. That's the x component of the velocity and then integrated over the cross section dy, and there is a width which I can take outside because I am considering this problem to be two dimensional. So the flow rate per unit width or the flow rate multiply is equal to the width integrated 0 to h, and the velocity profile was del P by L 1 by 2 mu y h minus y dy. So W del P by L into 1 by 2 mu 0 to h y h minus y square, sorry, minus y square dy. So W del P 2 mu L y square by 2 h minus y cube by 3. So I will have the flow rate as W del P by 2 mu L. This would become h cube by 2 and minus h cube by 3. So that is h cube by 6. Del P by L W h cube just make sure we have all the terms. So del P by L W h cube by 12 mu. So that's your relation between the flow rate, pressure drop and the geometry of the problem. So now you can see that if you were to fix the flow rate, you will have a certain pressure drop, or if you were to fix the pressure drop, you are going to have a certain flow rate, because you can use this flow rate in order to compute what is the average velocity. So the average velocity would be the flow rate divided by the cross sectional area. The cross sectional area is WH, so that is del P by L h square by 12 mu. And if you go back to your expression for the velocity, if you ask where is the maximum, so in this particular problem the maximum is at the center line. So you can compute this at y equals h by 2, which is del P by L 1 by 2 mu h by 2 into h by 2. So that is del P by L h square by 8 mu. Which is two-thirds of the maximum velocity. So you have now ways of thinking in terms of how the flow rate and pressure drop are related. So there are various such things that you can do. Now you can also think in terms of that if you were to plot a relation between the pressure drop versus flow rate, you have a relation which is linear here, that if you keep increasing your flow rate, you are going to get a higher and higher pressure drop. Now this is all within the assumptions of the flow being steady, the flow being fully developed. So when you further study this problem where you think in terms of that if the flow starts to no longer obey these assumptions, so if you continuously keep increasing the flow rate or if you continuously keep increasing the pressure drop, you will basically observe deviation from this particular relationship. You will start seeing that there is a certain deviation that you actually get in terms of what is the relation between your pressure drop, because you can write your Q as U average times WH. So then this becomes del P by L WH cube by 12 mu. So this then becomes U average is equal to del P by L into H square by 12 mu. And now you can try writing down a Reynolds number, which is U average L, oh sorry, we'll use H here. So U average H rho by mu. So rho U average H by mu is del P by L into h square by 12 mu let me just so u average del p by L h square by 12 rho u average h by mu is into rho u average h. Now this is my Reynolds number. So I have u average square del p by L into h by 12. I'll take the rho to the other side, and this quantity is Reynolds number. So del p by half rho u average square will be 24 by Reynolds into L by H. So this gives you a relation that if you plot a non-dimensional pressure drop, if you are looking at a non-dimensional pressure drop as a function of Reynolds number, then you will see on a log-log scale that it goes as 1 by Reynolds. So from this channel flow exercise, you are able to now obtain that as you keep increasing the Reynolds number, so the Reynolds number is a non-dimensional measure of your flow rate. The pressure drop keeps decreasing in this 1 by Reynolds or 24 by Reynolds being the precise term in terms of its variation with Reynolds. Now beyond a certain Reynolds number, the assumptions that we have made, they start to break and you don't see any further decrease in this 1 by Reynolds kind of a behavior. And that decrease is where all the assumptions that have been made break down, and we have a transition from the state that was a nice rectilinear, fully developed, unsteady, steady problem transitions to a turbulent flow. So we are continuously going to focus on this regime, but it is important to understand that the results that we have obtained, when we plot them in this dimensionless version, you will obtain a relation from the calculation in class, which is going to be very good as a way to measure the non-dimensional pressure drop given the Reynolds number when the flow is nice and laminar, which is within the assumptions that we have. Okay, so I'll stop here.